1 pound mole of carbon weigh in units of pound force? 12 pounds force. Why? So if the molecular weight of carbon is 12 grams per gram mole, then 1 pound mole of carbon is going to weigh, or is going to have a mass of 12 pound masses. And 12 pounds mass weigh 12 pounds force. Okay. Identify each of the following as C for capital cost or O for operating costs. A, operator wages. Operating costs. B, raw materials. C, equipment purchase. Okay. Does anyone not understand why any of those are classified like they were? No? Yes. Yes. So the raw materials that go into your chemical process, you need to keep buying them, right? To put them into the front of the process, to turn them into whatever you're turning them into. So that is why they are operating costs. You have to buy them again all the time. Okay. And finally, choose 2 independent equations that can be used to solve problems related to the system below. So here's our system below. We have a mixture of A, B, and C going into here and being separated into A and B and C. To get equations to solve problems about the system, what we would do is do balances across the system. In order to use, so those balances turn into equations. But in order to use those equations together, we can only use them together if they're independent from each other. Okay, so there are actually 2 right answers here. Who knows what they are? So I have anyone who, okay, thank you.
1 and 2 and 2 and 3.
1 and 2 and 2 and 3. Would you like to explain to me why 1 and 3 are not independent?
Because they both use A.
They both use A. One is just the mass balance, and the other one is the mole balance. The mass and the mole balance are the same species, are not independent. We talked about that in last class, and the reason why is because if you have this, all you have to do is multiply it by the molecular weight to give you this. You're not using them, putting them together doesn't give you any more information. They're not independent. This one is just a mass balance on the C. So you can use a balance on C with a balance on A. And what does X mean? X means mass fraction. In this class, X symbolizes mass fraction. Therefore, this is the mass fraction of C in stream 1. Multiply it by the total mass of stream 1, which actually you normally just call it M1. I put the total in there to help y'all. You get the mass of C in stream 1. So it's the same as this for A, it's just written in a different way. Yes?
Wait, is that mass flow rate or is it mass?
This is mass flow rate. The dot is for flow rate. Any other questions about that? Yes?
For number 1, you check multiply LDMs by their LDMs.
So remember this. This is a reason why the pound mass, pound force thing can be confusing. I will show you in here. Okay. We define 1 pound force so that 1 pound mass weighs 1 pound force on the surface of the earth. That is how it is defined. So I say, I have 50 pound masses here. How much do they weigh? They weigh 50 pounds. What that means is that if you are doing conversions or math with it, you have to use this right here All right, that I will show you on Excel, since today is about Excel actually. So, force is equal to mass times gravity, or mass times acceleration, but we're talking about mass times gravity for weight, right? Yeah? Actually, I'll call this W for weight. Yes, it does. So let's say we have 12 pound masses. That's our M. And then G is 32.2 feet per second squared. Okay? So our weight of our 12 pound masses is equal to, okay, 12 times 32.2, and that's going to be in units. This is not in units of pound force, not yet. This is in units of pound mass feet per second squared. We know those are the units because we haven't converted to pound force yet. Okay? So to get to pound force, we're going to use our conversion factor, which is that 1 pound force is equal to 32.2 pound mass feet per second squared. You should already be seeing what's going to happen. Okay, so we have pound mass feet per second squared. We're going to have to divide it by the conversion factor to get our pounds force. So, that is why that makes sense. So you can go through the conversions and you will see you will get to the same answer as if we had just said it's 12 pound masses, that means it weighs 12 pounds force. Yes?
So if this was a different planet,
In a different planet, it would be different. On the moon, yes. That's why I always say it's defined as on the surface of the Earth. Mm-hmm. Okay. And the other example, besides being on a different planet, is sometimes you're on, say, like a train that's accelerating, and you would want to use the acceleration of the train instead of gravity. But there we go. Today we're going to be talking about spreadsheets and graphing. And instead of a PowerPoint for today, I made y'all a handout. You have it? Okay. So, if you brought your laptop, bring it out. You can play with things. If you do not have a laptop, try to sit beside someone who does. And we're just going to, I'm going to show you some things that you can do with graphs for a while. And then with the rest of our time, I want you to ask a few questions about the homework and Tuesday's lecture and things like that. Okay, so yeah, we use spreadsheets a lot. Here at BYU, we usually use Excel. It's what's installed on all of the campus computers, and it's pretty common outside as well. It's the most common spreadsheet program people use in the industry. And spreadsheets can be helpful in a lot of different ways. So just a couple things about terminology. Each of these boxes is a cell. Each cell has an address That address is in the top left corner right there. Okay? A7, B5, etc. Each cell has a value. The value is whatever is in the cell. In this case, it's 1. In this case, it's nothing. And finally, we can put formulas into these cells. So that's what I did here, for example, is I put formulas into these cells. So one thing, so like right here. So that's a formula, that's n times g. One thing that can be helpful is you can name the cells. You have to be careful to name them something that doesn't interfere with something else. Now I say this is equal to n times g. There you go. And then similarly, I can say this is equal to that divided by g. Oh, actually that doesn't. Yeah. Oh, yeah. That is equal to that divided by g. Okay. So that's helpful.
Is there a limit to naming cells, like what variables it takes?
If you try to name it something that's already another cell, like if you try to name it F2, it'll get mad at you.
Yeah.
Yeah. Okay. All right. So, I guess that cell up there is still pretty big, really small. Okay. Anyway, that says B6 right now. That says MG. Give me a second. I'm gonna. Okay. Bigger. Okay. So one thing you can do, I think I just made it fuzzier without making it easier to read. Anyway, so one of the nice things about I don't think that helped. Okay. So one of the nice things about spreadsheets is it allows us to make a lot of calculations very easily. If they're the same sort of calculation. So for example, in this problem, we've got a stream A containing a fixed amount of mass flow of species A and very little volume. And I have put, for right now, that mass flow of A to 10 grams per minute. Stream B contains water and can have a variable flow rate. Okay? So, the flow rate of B is going to be in liters per minute. The two streams are mixed. Calculate the outlet concentration of A. Okay, so what formula? So remember what we have here is the mass flow of A going in, the molecular weight of A, and then the flow rate of B. When we say that A has very little volume, what we're trying to communicate there is that we can take the volume of the mixture of A and B to be pretty much just the volume of B. So, what formula should I put right here, using what information we have on this sheet, to give me the molar rate of A, or the outlet concentration of A is what it actually is. You know what? Actually, I should do 2 columns. I'm going to do 2 columns. Okay? So this is the molar rate of A in gram moles per minute in this column, and then this column is the concentration of A, so the molarity of A. So what formula will give me the molar rate of A? Yes?
Would it be like, so the mass flow rate times the molecular weight divided, sorry, the mass flow rate of A times the molecular weight of A divided by the flow rate of B?
Okay, let's see. So the mass flow rate of A, that's going to be grams per minute. When we divide by the molecular weight of A, that's going to give us gram moles per minute. So so that's what we'll do first. And what I'm going to do is I'm just going to do it like this. Okay. So, mass A, I gave a name. I must have done that before. But I'm going to do something here. First, I'll show you what happens when I don't do it. So I do like this, and then I double click, and it got angry at me. Why is it angry at me? It's because when I pulled it down here, it changed the cells it was referencing relative to where that cell is. It was using relative references. Okay, so this one, for example, it's still using the mass flow rate of A because I gave it a name, so it's a specific reference. But then this just changes as we go down. So the way to fix that is either to give that cell a name, or the easier way a lot of times is I put a $sign right there in front of the 11, and what that means is that the 11 is going to stay the same. I've told it to stay the same. I do this. As you can see, it's the same all around, which makes sense because our mass flow rate of A and our molecular weight of A aren't changing. And then the next step, which is what you said next, is to get the concentration of A by taking our molecular flow rate of A and then dividing it by take that, divide it by the flow rate. So minutes are going to cancel out. We're going to get gram moles per liter, which is molarity. And there we go. Yes? You name cells by going up here, like here, going up and putting a name in the cell reference up on the top left. Okay? And so that's something I do sometimes, but it's also pretty easy to just put a $sign right there in order to make it a specific reference. Yes?
How do you, is the, like, grams per minute, grams per mole over on the left, is that in a different cell? Or how did you get it to only use the number?
This number right here?
Yeah.
Yes, these are different cells. Yeah, if you try to put a number and letters in the same cell, it won't read it as a number. And you won't be able to do math with it. Okay, so here we go. So one of the nice things about spreadsheets, as we say, is you're able to make these calculations very quickly. All right, by using the power of just dragging it around and using the relative references. Just a couple other demonstrations to show how that works. Okay. So this cell is referencing those two cells right there, right? That's what it references in this formula. So then if I drag it over to the left, now it's referencing those two cells. So it just changed the references relative to where I moved it. Other things that are nice about spreadsheets. So let's say now I'm interested in knowing this for some other mass flow rate. All I have to do is change this, and I change everything. Or let's say A is just some different molecule now. Boom. So easy. Yes.
Can you go over how you got those all to like calculate out?
Oh, okay. So this is what I did. There's a couple different ways you can do this actually. One way is to just take the corner of your cell and grab it with your mouse, and then just pull it down as far as you want. Like that. If I pull it down further, it's gonna freak out because now it doesn't have any values in this cell that it's dividing by. Yeah, so I just took the corner and dragged it. There's another way. So this is on Windows. I don't know about Mac, sorry. Control, Shift, arrow down, or boom. Anyway, what, Olivia, yes?
Yeah. Why did it work on concentration but not on the other one? You know, when you drag it down for moles of
Oh yeah,
A.
it does work on this. It's just that in this case, remember I made both of these are specific cell references, not relative cell references. They're referencing the mass flow rate of A and the molecular weight of A, and those are the same for every flow rate of B. And I didn't have to do this in different columns if I wanted. I could have done like what was suggested, and I could just be like, I could just say that divided by that, make it specific, and divide by that. Okay, oh, so I'm just going to do something. What I'm going to do is I'm double clicking there, it fills it all out. Okay, and as you can see, it's the same. In fact, I'll show you this. Yeah, so I'd say Control Shift down arrow to select this whole column. Now I'm deleting it. Now I select this cell, I double click on the corner, it fills it all in. Yes?
Just a question, you have that numbers list on column F. Is there an easy way to do that? Or
On column what?
Column F?
Oh, column F.
Yeah.
Flow rate of B. So this, so actually there is, because this follows a so this is the information we're putting in. It's not calculated, but there is an easy way to fill it in, and it's this. This is a simple pattern, 1, 2, so Excel can figure that out, and I can just double click there, and it fills it in. See? And it can do that for a few different simple patterns. If you do it, if I just do 1 and I do it, it's going to fill in 1. If I do like 1, 3, 5, let's see if they can figure that out. I'm not even sure. Yeah, it can figure that out.
Okay. How far down does it go filling it in?
So in this case, it fills it in. It can tell that I probably just mean to go down as far as the end of this column, so it just stops there. If I did it over here, let's see what happens. Yeah, over here it doesn't want to do it, but I can just drag it down however far I want. Okay. Now down here, I made a graph, because that is the other nice thing you can do in Excel. So that's the graph I made earlier. I'm going to make it again to show you how to make it. That's another reason we really like spreadsheets, is we can make graphs out of them. And graphs are a really great way of communicating information about trends, right? So instead of asking you, find this one answer and then you put a block on it, instead you can find the answer for a whole range of input values. This gives us more information. So what I'm going to do is I'm just going to select, so my x-axis is going to be the flow rate, My y-axis is going to be the concentration. That's what I'm interested in seeing. So I'm going to select both of these, like so. Okay? I selected them both using control. There's other ways you do it. I'm going to say insert, scatter plot. Here. Now I have a scatter plot. So I went to insert again, and then there are all of these charts right here, up at the top. And so I chose the one with the little points on it, that's the scatter plot, and then I chose this one. But there are other options too. I can turn it into this with a line, or this is just a line and not the points. This does straight lines in between all of them. So that is something you could do if you wanted. Scatter plots. Okay, so there's various different kinds of plots, which you can see there, which you can play with if you want. There's pie charts and histograms and bar charts. This scatter plot is probably the most common one we use, because it just shows us, we change this, this changes. Now right now, it doesn't look very nice. We don't like charts that don't have labeled axes. So what I'm going to do is I'm going to go to design, and there's different options. I'm going to go to quick layout. That's pretty easy. I'm going to do this. So I chose a layout that has titles for the axes. And I'm going to change this one to flow rate, and then I put the units. You should always put units on your chart. And this one, I'm just gonna say concentration, gramole minute. There are various things we can do here. Gonna get rid of those. And I'm gonna call the chart concentration versus flow rate. So I'm just going to show you a couple other easy things. I'm going to post this spreadsheet, and I want you to download it and just play around with it and see what you can figure out. We're going to do a lab in week after next where you have to make a chart. Let's see. So I'm going to change the y value to this. Now it's a line, which makes sense because it doesn't change, right? Or how about I make a chart with both of these on it? Let's see what that does. All right, see, now we have a chart with both the molar flow rate and the molarity on them. These are in different units, so this is not a great chart, but you can see how that works. Okay, so actually what we're going to do now is that we have a representative from Valero here for the career fair who's going to come and tell you a little bit about real world engineering things. Yeah.
Well, hello, my name's Ty Carlson. I actually just came from the 263 class where I was showing them some very useful things with this Excel. I mean, the Excel stuff that you learn, you will use throughout your career. So I will say, at least within Valero, the BYU graduates are known as like the Excel wizards. Because the 263 class in particular, when I was taking it, we learned VBA coding, very simple VBA coding. Some of you may already know a little bit of that. But those are really important skills that you have a foundation of here. I mean, you just learn very basic things here at BYU. But that's enough to, when you do need to use it, in, you know, in your job or whatever career you're doing, you have something that you can start with. And all you have to do, I mean, it gives you the confidence that if you see something where you can apply using some Excel spreadsheet or some simple coding to, you know, make improvements and whatever you're doing at work. I showed some spreadsheets to the 263 class that literally saved our company tens of millions of dollars a year. Because we're in the age where there's so much information and so much data that if it's not looked at properly, and especially if it's not presented properly, then there's nothing's gonna happen. And so it's really important that you learn how to present data and how to analyze data and how to manipulate data. And that's where EPA helps a lot. When you need to manipulate millions of data points, you gonna do that one at a time? No. So, that's not really what I came here to talk to you today about. I more just wanna talk about, kind of back to what I said earlier, you're learning the basics of problem solving in your classes here. And I wanted to show an example. This is literally something I was doing last week. Right now I'm an operations manager at a refinery in Southern California. And I have mechanical engineers that help me, I have some process engineers. So when you start, you'll probably start as a process engineer. It doesn't have to be a refiner, it could be lots of different industries. But so process engineer, we were talking about, we were having a problem getting flow out of a particular part of the unit. And have you done anything with flow yet? Pumps? I know you have a lab where they do something with the pump curve, right?
It's in a month.
Okay, alright, so this will probably make more sense in a month, but, so we're trying to pump this fluid and we're having high pressure drop. High pressure drop resulted in us getting lower flow rate. We couldn't pump as much as we should have. And so we were looking at the system, there's lots of things that could go wrong. We have a pump that's either not pumping the way that it should. There's control valves. The control valve regulates the flow of, it controls the flow. So if we want 1,000 barrels a day, this control valve can be set to control 1,000 barrels a day. And really what it does, it's kind of like your thumb over a hose. You know, you pinch back on your thumb, you can feel the pressure build if you try to pinch back too much. But it's the same thing a control valve does. It just pinches back, creates higher pressure drop, reduces the flow rate. So that's another thing in the system. And then it's going into a tank. And so what we're doing is we're trying to figure out where in the system do we have too high of a pressure drop. And really what you'll learn in your classes, you'll be able to say, all right, I have this pump. I should be able to determine how much pressure is this pump going to provide, theoretically. And then you should be able to determine, at this flow rate, what pressure drop should we see in this control valve, theoretically. And then what you do is you go out and you actually take pressure readings at multiple points in the process. And we were doing this and we were struggling, we couldn't find out what the problem was, and it wasn't quite making sense. And it all came back to, we had some bad assumptions. We assumed that our tank was at atmospheric pressure. It had zero pressure, it was open at the top. But we took all these pressure readings within our process unit, but the tank is thousands of feet away. Oh, and that's the other thing, you've got thousands of feet of pipe in between. And you can theoretically calculate how much pressure drop should you have in that section of pipe. And so, with the skills that you learn, you can determine, are we seeing what we would expect to see? And then you're out there, you're working with operators, you're taking, installing pressure gauges at different points in the process to understand where do we have a problem. But we didn't see any problem with the pumps. The pump was doing what we thought it should, control valve was doing what we thought it should, the pressure drop through the pipe was what we thought it should be. And that was the key. So the pressure drop through the pipe was what we expected, but the pressure at the tank, which we expected to be pretty much zero, ended up being like 170 pounds. Like, why? That doesn't make any sense. So actually this morning at work, they're in the process of determining if our tank is full of sludge that has built up and blocked the like where this flow goes into the tank. And so, and these are all things, you have there's lots of things that you don't know when you're dealing with the process. There's always things that you don't know. And you can't just shut things down and open things up to figure out what's going on, because we have a process we're running. A lot of times if you shut one thing down, you're shutting down an entire process that could cost, $1 million a day. So it's being able to diagnose and determine with the skills that you're learning, and this will probably make more sense, when you learn about pump curves in your lab. You'll understand that as a pump pumps more and more flow, it provides less pressure. The less flow it provides, you get a higher pressure. So that's another thing we were dealing with, is on this pump curve, were we where we expected to be? So that's just, I wanted to give a real world applicable example of the types of things that you'll be applying when you do get out into the field and start working. Because it's exciting, it's fun work, it's challenging, it's not monotonous, there's always something that's broken, something that needs solving, and that's why we need good, smart engineers.
And I really like that story as an example of problem solving, which we talked about last week. Do you have an info session you'd like to do?
Yes, so there is an info session that, so we're gonna be looking to hire probably 10 interns next year. We hire, sometimes freshmen, sophomore, and junior interns. And so our info session is at 3 o'clock in 256 of the Clyde building. And I'm also speaking at 11 at an AICHE, I guess they're having like a guest lecture or something, so I'll be there. That'll just be kind of an open question. I have some things I can talk about, but I was opening up to questions, whatever you guys want to ask or whatever you're interested in.
What is it again?
So the info session is at 3 o'clock in the Clyde building, room 256. And then the AICHE thing is at 11 o'clock, also in the same room, 256.
And we
Clyde, yeah.
We very, very, very much encourage sophomores and juniors in particular to try for internships. But freshmen, I think it still could be good for you to go and talk to people and figure out and learn things about the process.
Especially as a freshman, I know like a job right now is probably the first thing from your mind. You're probably starting your first semester of your freshman year, right? So, but what you want to do is you need to go to the career fair, and you need to get comfortable talking to recruiters, because you're gonna mess up. You want to mess up now when it doesn't matter. You don't want to mess up when you're a junior or senior looking for a job, and that's your first time trying to talk to a recruiter. You want to be comfortable talking to recruiters with that. So I just encourage you to, don't be afraid or don't hesitate to go and go to the career fair and just explore options. You probably don't even know what part of chemical engineering you're interested in, but the sooner you know what you might be interested in, the sooner you can start to ask questions of particular companies, and the better off you'll be.
All right.
Thank you.
Thanks, everybody.